evening students, myself Nupur Mittal. Today I am going to talk on time response analysis. So these are the basic content. In the previous lecture I have talked about the time response of first order system, and today I will talk about the time response of the second order system, right? Let me first take the pen, okay, and particularly I will talk about the second order, the time response of second order system when the step input is applied at the input terminal of the control system, and in after that we'll talk about the time domain specifications of the second order control system. So today actually I am going to give you the expression for the second order control system. So before talking about the response of the second order system, I would like to recall you how to find out the second order, how to find out the second order of a system, whether it is second order, third order or whatever. So second order system can be defined as the system in which the highest power of s in the denominator of any transfer function is 2, right? Like this, like if I have the transfer function is equals to 2 upon s square plus 3s plus 4. In this case, the highest power in the denominator of this transfer function is 2. So this is called as the second order system. So similarly, I can define the block diagram of the second order system when, let's say, Rs is the input applied to any particular system, and we have here let's say it is a unity feedback system and a negative feedback is applied to the system. Cs is the output of the system and this is the Gs, where the value of Gs is omega n upon s into s plus 2 zeta omega n, where this omega n is the natural frequency of the system, right? And this zeta is representing the damping factor. It is representing the damping, that is oscillations produced in the system. I will discuss about these factors in next lecture. First of all, let's move ahead and let's find out the transfer function for this particular system. So as we know, this is GS, that is forward path transfer function, forward path gain, and here HS is equals to 1. So we can write CS upon RS will be equal to GS upon 1 plus GSHS, right? Now here we can put the value of GSHS. The value of GS here is omega n upon s square plus 2 zeta omega n s, and similarly 1 plus omega n upon s square plus 2 zeta omega n into s, right, into 1. After solving this, we will get the value of Cs upon Rs, that is the transfer function of a second order system, will be omega n square upon s square plus 2 zeta omega n s plus omega n square. So this is the standard transfer function for second order system, and I will use this standard function for solving the numericals, right? So let's move ahead when different inputs are applied, right? So from this transfer function, the response of the system will be equal to Rs into omega n square upon s square plus 2 zeta omega ns plus omega n square, right? So the response of the system will be Rs into omega n square upon s square plus 2 zeta omega n s plus omega n square, right? When a unit step input is applied, that means RT is equals to 1, or we can say Rs is equals to 1 by S to this system. Then the value of CS will be 1 by s into omega n square upon s square plus 2 zeta omega n s plus omega n square, right? We can rewrite this denominator. So as to get the perfect square, because in future I will go for the partial fraction of this term. So rewriting the term s square plus 2 zeta omega n s plus omega n square as s square plus 2 zeta omega n plus zeta omega n whole square, okay, and minus zeta omega n whole square. What is left here? Plus omega n square, okay. So we can take this term as one term and we can take this term as another term. So we can do it like write it as s plus zeta omega n whole square and plus omega n square 1 minus zeta square. So this term, this denominator can be written as like this. So now CS will be equal to 1 upon s into, okay, into omega n square upon s plus zeta omega n whole square plus omega n whole square 1 minus zeta square, okay. Now taking partial fraction of this equation, while doing partial fraction, we will get doing partial fraction of above equation, okay, I will get CS is equals to, okay, it will be 1 upon s minus s plus zeta omega n upon, I will write it directly, okay, you can do the partial fraction. I am writing the value of the a and b as constant directly. It will come out to be zeta omega n whole square plus omega n square 1 minus zeta square, like this, okay. Now I need to take the inverse Laplace transform. For that I have to rewrite this term, okay. I have to rewrite this term. It come out to be 2 zeta omega, right? So I will rewrite this term as 1 upon s minus s plus zeta omega n upon this term. This term will be s plus zeta omega n whole square. This will be, the whole square is outside, plus omega n square 1 minus zeta square, okay. Now I am left with minus zeta omega n and the same denominator, that is s plus zeta omega n whole square plus omega n into 1 minus zeta square, okay. Now put omega d is equals to omega n under root 1 minus zeta square in the above equation. Okay, here omega d is the damping frequency of the system. So Cs will be equal to 1 upon S minus S plus zeta omega n upon S plus zeta omega n whole square plus omega d whole square. Right, one term is this. Another term will be, in this term I am going to multiply and divide the term omega d, so that I will get, when I will take the inverse Laplace transform, then it will become the cosine term. So here, along with zeta omega n, I am going to multiply omega d and divide it by omega d. Okay, so this will come out to be the sine term, sorry, S, this will be S this is coming out to be S plus zeta omega n whole square plus omega d whole square. Okay, now taking the inverse Laplace transform of this equation, I will get, now when taking inverse Laplace transform of the previous equation, I will get C t is equals to 1 by S means minus k1, okay, and that was e raised to the power minus zeta omega n t, and the term is cosine of omega dt minus, there we have zeta omega n, right, and it will become e raised to the power minus zeta omega n t sine of omega d t. Okay, so let me check once. So this will become e raised to power minus zeta omega n t cosine of omega dt, and this will become zeta omega n upon omega d. Okay, and this will become sine of, so it will be upon omega d. Okay, now putting omega d is equals to, again back, omega n under root 1 minus zeta square, right, and I am writing here itself. Okay, this will be omega n under root 1 minus zeta square, so that omega n will get cancelled out. Now I will take from this e raised to the power minus zeta omega n t as common upon under root 1 minus zeta square as common from this term. So this will be e raised to the power minus zeta omega n t upon under the root 1 minus zeta square will be common from this term. Now I will left with under root 1 minus zeta square into cos omega dt, right, minus of zeta sine omega dt. Okay, this is the thing. Now let 1 minus zeta square will be equal to sine phi t, sine phi, I'm sorry, this is sine phi, and let zeta is equals to cos phi, and put this value in the above equation. So Ct will be equal to 1 minus e raised to the power minus zeta omega n t upon under the root 1 minus zeta square, right, and we will get here sine phi cos omega dt, right, minus cos phi sine omega dt. So it will become the formula of sin A cos phi minus cos A sin phi. So this formula will, see, we have sin A plus B will be equal to sin A cos phi, sin A into cos phi, right, minus cos A into sin phi. So this is the formula for sin A plus sin B. So we can write it as Ct is equal to 1 minus e raised to the power minus zeta omega n t upon under the root 1 minus zeta square into sin omega d t plus phi. Okay, where phi is equals to, tan inverse of under the root of 1 minus zeta square upon zeta. Okay, and omega dt is omega n under root 1 minus zeta square. So final expression for Ct when step input is applied to a second order system will be 1 minus e raised to the power minus zeta omega n t upon under the root 1 minus zeta square into sin omega dt, I am expanding it again, into t plus tan inverse under the root of 1 minus zeta square upon zeta. So this will be the final expression for second order system when a unit step input is applied at the system. Okay, so correspondingly this response reflects that the graph will be of exponentially decaying in nature, right, which is having a frequency of omega n under root 1 minus zeta square with a time constant of 1 by zeta omega n. So we can draw the graph for this system when a step input is applied. The graph will be exponentially decaying in nature. This is the graph that we will receive, and where this is 1 unit, okay, and this is 0.98, and this rest is 0.2. It is around at 40. Okay, and the time constant here will be equal to 1 by zeta omega n. Okay, so this is the response of the second order system. So this response is basically for zeta less than 1, that is underdamped system. Okay, so we have the response of the system. We know the input is 1. We can calculate the error, and finally we can calculate the steady state error. So error will be, for this system, the error will be equal to RT minus CT. Okay, so RT here is 1. So ET will be the error will be RT minus CT, and here RT is 1, and we can put the value of CT, that is 1 minus e raised to the power minus zeta omega n t upon under the root 1 minus zeta square into sin omega d t plus phi. So ET come out to be 1 get cancelled, right? And Et will be equals to e raised to the power minus zeta omega nt upon under the root 1 minus zeta square into sine omega dt plus phi. Here this is t. Okay. Similarly, steady state error can be calculated. Steady state error will be equals to limit t tends to infinity. Okay, t tends to infinity e raised to the power minus zeta omega nt upon under root 1 minus zeta square sine omega dt plus phi. Okay. So this is the case when zeta is less than 1, that is underdamped case. We say that we have obtained the exponentially decaying graph which is for underdamped system. Now we can go for undamped system where zeta is equals to 0. You can say this will be the case 2 when zeta is equals to 0. This system is called as undamped system. Okay, so we can simply put the value of zeta is equal to 0 in the response of the second order system. So response of the second order system is Ct 1 minus e raised to the power minus zeta omega nt upon under root 1 minus zeta square sine omega dt plus phi. Okay, when I put this value here, we can put the value of zeta is equals to 0. So where here I'll put the value of phi here, that is tan inverse under root 1 minus zeta square upon zeta. Okay. Similarly, I can put the value of omega d, that is omega n under root 1 minus zeta square. So it comes out to be Ct is equals to 1 minus e raised to the power, it becomes 0, okay, upon under root 1 minus 0 again, then sine omega n under root 1 minus 0 into t, right, plus tan inverse under root 1 minus 0 and it is upon 0. So it is coming out to be Ct will be equals to 1 e raised to power minus 0 is 1, right? So 1 minus sine omega nt, right, plus pi by 2. Since tan inverse infinity is equals to pi by 2. So it can be written as Ct will be equal to 1 minus cos omega nt. Okay. This is the case when the value of zeta is equals to 0. And we get the expression, we get the curve as first step input only, we will get this curve. Curve will be like this. Okay. Similarly, for zeta is equals to 1, this is called as the case of critical damping. So in critical damping, we will get the value as for step input, that is 1 Ct. For critical damping, we will have the graph like this, okay, where this is 1 unit, okay, and this is 0.98 and the rest one is 0.2. Okay, it is around at 40. Okay, this is the graph for zeta equals to 1. This is the graph for zeta equals to 0. Now, similarly, when we talk about zeta greater than 1, that is overdamping case. In case of overdamping, we will get two time constant. One is at faster rate, one is at slower rate. So faster rate damping factor will be cancel out and we will get the response as a sluggish response will be received in case of the overdamping. This is 0.2 and this is 0.98 and this whole is 1 unit. Okay, this is around 40. So this will be the case for overdamping. In the next lecture, I will talk about the time domain specification of second order control system, which are rise time, spread time, delay time, okay, and the peak overshoot. And this is it for today's lecture. Thank you.